on this computer. So heap sort has two phases. First phase called heapify, which is where we take the array we want to sort and turn it into a heap, specifically a max heap. And then the second phase is remove the thing from the max heap and put it at the end and pretend to remove it, but actually move it to the end and pretend it's out of the heap entirely. And just keep doing that until we've done that to all the items in the heap. And then and as a result, we'll get since we've gone from the biggest item to the smallest item, we've got a sorted array. So it's pretty cool. I mean, this is circuitry stuff, but like something in this class, it's a quarter of this exam. That's pretty cool. But let's look for something that's maybe a bit more relevant to our, not interest per se, but our experiences. Merge sort, they like sorts. Everybody likes sorts. They're good questions. There's one exam. I know I'm not just seeking blindly. There we go. Hey. Answering the following questions about a binary search tree. So here the height of a tree is defined as the maximum graph distance from one node to the leaf node. For example, with a node of no children is a height of 0. Now that is different than the height we define a tree as, right? For me, like if you're a single node, right, your height 1. If you've got a child, your height 2, 1 level, 2 level. What they're defining it is the number of, I define the height as the number of nodes, numbers of layers of nodes. They're defining their height as the number of layers of edges. This is perfectly fine. These are different interpretations of something that is valid. I like using height as my equation because that allows me to do a very easy math equation without any wonky adjustment, which is that a perfect tree of height h has 2 to the h minus 1 nodes in it, right? I like that definition. Here they're saying that, we'd have to add 1 to that. That's okay. That's fine. This is a perfectly reasonable interpretation. Just, when we deal with our assumptions, we want to know. But just know on my exams, when I'm talking about height, this is a height 4 tree. They're saying that this is a height 3 tree. I think this has become because we're coming from two different worlds. All right. So one question, so these are the kind of questions you'll experience on the exam. So let us apply the following operations to the tree above to the tree in the order shown. Specifically, these are the operations you would see on the exam or these were the questions you would see on the exam if I were actually to make you, sit down and draw, but it's going to be electronic. So I can auto grade, which is faster. Okay, so inserting 3 to this tree, right? We want to insert 3. 3 is less than 9. It's less than 4. It's greater than 2. So 3 goes here, right? Makes sense? Okay, inserting 8. 8 is less than 9, greater than 4, greater than 7. Oh, there's an empty space for it. So we're going to put 8 there. That's how all adding is. Adding is fairly straightforward. Adding for an unbalanced, for a regular binary search tree, one that doesn't self-balance, which is pretty much all the trees I'll be testing you on, right? The adding a node is never going to adjust the structure of a tree. On the other hand, our remove operations, delete, will adjust the structure of the tree. So here it's asking us to delete 4. Now the way we do that depends on basically how many children I have. Deleting a node with no children, right? Like this guy, super easy. We just simply remove him, blot him out, because there's no need. We just don't need to do anything with the structure. If, on the other hand, I'm deleting a node like 2, that's also not too bad. What we do is that we promote 3, have 4 adopt 3. That's not too hard. Basically, 3 would replace 2 as the child of 4. The issue the trickier one is when we have to remove a node with 2 children. Now to do that, because we have to replace it with a node that keeps the binary search tree property. So we have to replace 4 with either the smallest thing that is biggest, the biggest thing that is smaller, or the smallest thing that is bigger. So in other words, replace it with the next in order, the node that comes directly before 3 in the tree, or the node that comes directly after it. So either 3 or 6. I generally go with the in order predecessor, which means that to find that, right, in any tree, to find in any tree where I need to find the smallest thing that's bigger, what I do is I have to find, sorry, the smallest, the biggest thing that is smaller, I should say, the biggest thing that is smaller. So I look at all the items that are less than me, and to find the biggest one of those, I go all the way to the right. So I step 1 to the left and go all the way to the right. That is how I find the biggest thing, right? Make one zig and then zag as hard as you can is another way to put it. If you can't zag because there's no nodes to zag to, if you can't go to the right because you are the biggest thing in that smaller tree, then that's it. But anyway, let's go ahead. So here in this case, by deleting with this delete operation, what we're going to do is we're going to replace 4 with 3 because that was 1. We would go all the way to left and all the way, sorry, 1 step to the left, all the way to the right. So replace 4 with 3. Now to delete 9, we're going to see that again, right? We go 1 to the left to go into to get to the area where all the things that are less than me are. And now I need to find the biggest thing, which goes all the way to the right. Now that works because if you're bigger, you get put to the right. The biggest thing is found by going all the way to the right. And we know that this thing all the way to the right is the biggest because if there was another item to the right, it would be even bigger. And if I have a left child, well, it would be smaller than this thing. So that can't be bigger. So we don't have to worry about that. Make sense? Right? That was a proof spoken in plain English. So we go all the way to 1 step to the left, all the way to the right, until we replace this guy with 8. Sorry, we replace 9 with 8. Okay, and so that's the way our tree would look. Oh man, that annotate tool is useful if you've got a pen. All right, so answer the maximum and minimum height tree heights of a binary search tree with n nodes, right? So this one's pretty cool. This one's pretty cool. So again, I'm going to use n is equal to 1. N is equal to, sorry, the minimum and maximum tree heights. Again, I'm going to use this my definition of height, which is the number of nodes. So this is a tree of height 1, height 2. This is height 3, and this is height 4. Okay. So if I've got n nodes, so if I've got like so let's go ahead and say I've got 7 nodes. What is my maximum height? What is the biggest this tree could be? The tallest the tree could be? Absolute, yes? 7. Yeah, that is correct. Because if I've got 7 nodes, my tree could be really ugly and look like this. 1, 2, 3, 4, 5, 6, 7, which is essentially the way that a tree could get to the biggest height is if you're just essentially a linked list with extra steps. Okay. It could also have just been a straight diagonal line, but I wanted to mix it up a bit. It was more fun to draw out that way. So anyway, so minimum height. Well, the minimum height would be essentially a perfect tree, right? Because perfect trees are basically as filled out as much as possible. They are, or more specifically, a perfect tree. The minimum height would actually more look like a complete tree, which a perfect tree could be, a perfect tree is a complete tree, but basically where everything is optimally placed. So what is the maximum height there? So if I've got n, so, right, we've already kind of worked on that equation, which is that if I've got if I've got a perfect tree of 2 to the h minus 1, that means that it will have n nodes, right? So think about that. If I've got a tree of height 3, perfect tree of height 3, I've got this guy. Okay. This is a tree of height 3. The number of nodes in that is 2 to the 3rd, which is 8 minus 1, which is equal to 7, which is exactly the number of nodes I have in there. I know my handwriting is terrible. Deal with it. Okay. Well, actually, probably be better if I actually made the line thicker. Yeah, that would work much better. Okay, so what is the maximum height? So what is the minimum height? The minimum height would be, I guess, so if I've got n nodes, then I would guess it would be log base 2 of n. One plus log base 2 of n. So let's see if that works out. So if I've got no
log base 2 of
n plus 1.
There's 2 to the h minus 1.
2 to the h minus 1, maybe. But here's the thing. What about what if I do a note? What if I drew this tree inside the square? I mean, there's nothing stopping me from adding floor or ceiling operations, which I should do because, you know. So what is log base 2 of n plus 1? So that in that case, it would be, you know, so that would be height of 1. So we're passing 0. Those are outliers. I'm not going to worry about it too much. Point being is that let's go ahead and see log base 2 of n, and then if I floor it, right, which just means round down, right? Just forcibly round down when it's not, we're not at a whole integer. So if I pass in, yep, we want n plus 1. So if I have 9 nodes, right, what it's going to do is I'm going to say, okay, so if I have 8 nodes, this becomes 9. Log base 2 of 9, well, that's a hard thing to do. What's log base 2 of 8? Because that's what we're going to round down to. That's 3. So the height of this thing is 3, so that we don't want that. What we want is ceiling, so that will round up. I don't know these things off the top of my head, at least not that one. I don't really deal with the mathematics too much. So these are kind of the fun, but anyway, these are the kinds of questions that you would be able to answer if you've been practicing for it, and God knows you'd practice for an exam, right? So, but it's not really that far out, and these are the kind of questions that you know, that interview companies really like to deal with. Another one would be, you know, here's another one that's kind of, if you want to practice for an interview style question, which is suppose you have tree A and tree B, right? Write a function that determines whether and A is a much bigger tree than B. Determine whether, write a method or a function or whatever to determine whether or not B is a subtree of A. Right? Does B contain does A contain B as a subtree? To which, of course, you can ask elaborations. Do you mean like it's got to look exactly like this, or can A have can it have that structure as well as a couple nodes dangling off of it, right? So you're allowed to ask for elaboration on those kind of things, which does change the nature of the problem. So, but you know, trees are great because they deal with references and recursion. So of course they're naturally kind of good interview questions. All right, any questions from the Zoom gallery?
I'm pretty good, thank you.
No worries. All right, again, in case you're curious, by the way, for the people who are not seeing the Zoom gallery, because again, 2 monitors allows me to keep my screen clear of the Zoom stuff. We have 4 people in Zoom session right now. Okay. If you don't feel up to coming for class for whatever reason, you know, especially if you're sick, just, you know, Zoom in. It's no problem. Just send me a message to make sure I do start that Zoom session. Okay, I really value you being healthy, because if you're not healthy, you can't work on this stuff. And if I'm not healthy, Well, I'll be miserable. And you don't want me to be miserable while I'm grading your work, right? If I'm miserable while grading your, yeah, it's got us missing a semicolon, 0. Yeah, so just don't get me sick. All right. So, all right. That's it for like what I wanted to cover. Just I will cover this stuff in more detail, and I'm happy to go. If you go searching for other practice problems or interview questions, I am happy to help. If not answer them, at least point you in the right direction to get those solved. Because there's no guarantees that I can always solve any interview question. There are questions I can't solve. I'm not an infallible human being. I just happen to have had lots of exposure to a lot of different problems. But if you've got questions related that are data structure adjacent, I'm happy to answer those too. Okay. So let me go ahead and end my recording.